So, hello everyone. My name is Madelyn. I am an engineer at AWS and one of the two Valkey maintainers here today. The other one is Victor, kind of sitting up in front. So I think I recognize a lot of you. So I was just going to ask, who here has not heard of Valkey before? Excellent. So one person's lying to me. Cool. I'm going to give a very brief introduction to make sure we're all on the same page, but most of this is going to be focusing on what's new in Valkey 8, which is the new release of Valkey we launched on Monday. And I'll be diving a little bit into the technical details of all the implementations, as well as kind of why we built the features that were built. So if you have any questions, I think it makes sense to sort of ask them interactively as opposed to wait till the end, because if you have a specific question about a specific feature, it kind of makes sense to just kind of ask it at the time. So small room, raise your hand, I'll repeat the questions, but there will be some time at the end as well. So as I said, Valkey, it's the open source fork of Redis. The license change happened back in March of 2020. We created Valkey 7.2 in April, and now Valkey 8 just launched recently. As we said, it's fully compatible because it's a fork of Redis, so all the code base is roughly the same, backed by the Linux Foundation, and it's maintained by more or less the same set of developers that were maintaining Redis before. So I said that me and Victor are two of the maintainers. The other four maintainers who are not here today are Zhao Zhao, who's from Alibaba, Ping Shi from Google, Wen from Huawei, and then Zhu Binbin from Tencent. So these are the 6 folks. You can see that a lot of them are from the various cloud providers. I am hopeful that we'll be able to expand this group sometime in the future. So if you're interested in contributing or see any of the features up here that you would like to help extend or make better, we would love to have more people get involved in the project. So that's sort of my little introduction spiel about the project. So let's talk a little bit about what we try to do with Valkey. Yeah, I took your slides. They're great. We like to think of Valkey, Valkey is primarily an in-memory first database. So if we compare this to more of a traditional database, which writes more to disk, it focuses more on, strong durability and often is a lot slower because of that reason. So the most common use case that we're trying to optimize Valkey for is basically for in-memory caching. So the main things we're focusing on making sure it's very fast. As opposed to having complex relational queries, you have simple key value lookups. So we have a primary hash table, which we'll talk about quite a bit. And we want to make sure that's sort of as fast as possible and as efficient as possible. Since when doing point lookups, you want that to be fast because that's the main use case we see. And the main storage is going to be volatile for this purpose, since we don't actually need the cache to be super durable. But we do try to preserve data where possible, since if your cache loses all its data, then you have a bunch of cache misses. And so Valkey does that through replication. So, and I guess like AWS storage, append-only file storage. So we replicate data both to disks as well as to other nodes in the cluster. And these are basically extra backups of the data, but this is all async replication. So unlike something like Postgres, which has synchronous replication, once you write to the primary, it makes sure it's also written to the replica. We don't make those guarantees unless I guess you can configure it to sync the data after every write. But most people run it in an async mode where you get the acceptance back for the writes and then flush the data. But we also try to make sure Valkey supports a bunch of different workloads. Valkey has a lot of other things like Lua scripting, pub/sub advanced data structures like geo and extensibility with modules. So we want to make sure that all of that is working for the beyond caching-like use cases. Some people do use Valkey as a primary database, and we want to make sure that all of those workloads are continuing to work as expected. So in a sense, this is going to be the agenda slide for today. This is kind of the roadmap we had for Valkey 8. I talked about this briefly. Who here went to the talk on Tuesday? Okay, so this is mostly new for most people. Cool. So these are the main 5 pillars that we sort of focused on with Valkey 8, and I'm going to go over each of them, and then I'm going to go dive into each of these specific features in a lot more detail. So The first pillar that we had was for performance, which was we improved the multi-thread performance of Valkey. As we talked about with caching, it's very important to have fast point lookups. So we introduced a improved IO threading architecture, which basically gives us up to about 230% more performance by adding additional cores. So this allows you to a little bit to vertically scale the system without having to move to something like Valkey cluster mode or re-architecting to sort of do your own, sharding on the client side. So we also, in the performance bucket, we also improved client support with, we added an experimental feature called RDMA support. So RDMA, I think it stands for remote data memory access, but I don't actually remember. The idea is that instead of using TCP to access data on another machine, you're able to basically send a memory access to another machine. And so clients are able to basically create a command locally in memory and then tell Valkey to pull the data and then execute command. We saw really good performance improvements without adding additional cores with this feature. But the system you're running on does need to support RDMA. So it is currently an experimental feature, which is a new thing we're trying with Valkey 8 that wasn't very popular in Redis, which is that it requires a build time feature. So if you are interested in it, you have to go pass in a flag when you build it and try it out. Right now, there's only one client that supports it, which is the C client, libvalkey, as well as I think the C++ client, because it's built on top of it. So we're trying to kind of get some people to test that to see how that works out for the future. So I think a lot of people intuitively understand why performance is important, which is sort of why I don't want to say it's like the main pillar that we've been pushing a lot for this project, but this is like the main thing that we've been talking about with Valkey 8. So the next pillar that we kind of focused on was efficiency. So we wanted to improve the memory density. So if you're using Valkey as a cache, you'll often be kind of tracking like your cache hit rate in the database. So when you do a query to the database, you'll cache it in Valkey. And the more queries you can cache in the database, the higher chance that the data will be there on subsequent accesses. So we thought it would be very important to try to reduce some of the overhead within the main hash table. So I'll talk in a little bit more detail about how we did this, but we got about a 20% reduction in overhead in the best case, which is when you're using Valkey cluster, since we removed a lot of overhead in cluster mode. But we also removed about 8% of overhead for basically all applications. Cool. Then the next major pillar we had was reliability. One thing that you'll have recall is that with the TSC, a lot of them are from the managed cloud providers. So they all kind of care about running Valkey efficiently in the cloud. So a lot of folks were very incentivized to sort of improve how reliable Valkey was. And so when we talk about reliability, we talk about like when a failover happens, what's the chance, like how fast can it recover and get back to a steady state? What's the ability for clients to rediscover the system and be able to connect efficiently? So the two major features here is that we improved how slot migration works. So Valkey supports a distributed mode called Valkey cluster. So you have multiple different shards of data, and sometimes you need to move the data between the shards. So we call that slot migration or online resharding. And that operation was only coordinated between primaries. So if one of the primaries failed and a replica took over, that replica would be unable to continue the process. So we ended up with a lot of states where the cluster was unable to make progress and users would see downtime. The other thing that Valkey cluster has today is redirections. So if you try to talk to a replica, it will automatically tell you to talk to the primary to get the strongly consistent reads. So if you can read your writes, basically. So Valkey cluster came after what we call standalone, which is individual nodes. And so what we also implemented for Valkey 8 was the ability to redirect requests from the replica to primaries and standalone, which I think is only implemented in a couple of the clients today, but also it should reduce the amount of downtime that clients see during both managed and unmanaged failovers in the cluster. So those are the main features we had for the reliability pillar. The fourth pillar is replication improvements. So replication is when you have a primary and you're sending the data to the replica so that you can read from the replicas. So the main thing we focused on here was improving the efficiency of the full sync replication. I think I'll just kind of talk a little bit about that and kind of when I go into the details, but it basically makes the process almost up to 2 times faster, so that when you see a failure, you'll be able to recover about twice as fast. So the last pillar we had was observability. So these are all basically in 2 different buckets. The first is we saw a lot of our users complain about the fact that they have a lot of traffic or a lot of data, and they're not sure who's causing it or where it's coming from. So we had the ability for clients to determine like what are the most expensive clients or where most of the requests are coming from per client. So you can basically say like, which user is sending most of the traffic or causing most of the load on the server. So this is specifically useful if you maybe are more of a sysadmin type person who just have access to the cluster and don't necessarily know what the applications are doing. So you'll be able to figure out who's doing all the work. And then the other big improvement here is for cluster mode, which we've been talking about quite a bit, is that there's no good introspection on where the data is distributed across the cluster. So we've talked a little bit about shards. So in cluster mode, all data is mapped to what are called slots. There's 16,000 slots in a cluster. So keys are deterministically hashed to a slot. So like key foo might get mapped to slot 12,000. And so the clients basically figure out, they determine the slot of a key because it's deterministic, and then they'll go figure out which node has that slot and then go request it from there. So when you're moving data around, you need to move an entire slot atomically from one node to another. But there's no good process in 7.2 to basically figure out, is there a hot slot? Is there a cold slot? Is there a slot with, like, what is the right slot to move when you're like rebalancing a cluster? So we implemented what we call per slot statistics to basically figure out which slots are the like ideal ones to be moving around. So this is mostly for administrators to figure out where or how they should rebalance data during a slot migration. So these 5 pillars, we kind of picked these because, as you can kind of see, there's no net new features here. There is some little features in the bottom which are still cool and important. But we mostly wanted to, like when we launched Valkey 8, if someone was using Redis 7.2 or Valkey 7.2, they would feel very confident just kind of moving to 8. And hopefully they would see some type of improvement. Yeah. Yeah, go for it. As I said, whenever you want, ask a question.
So I'm intrigued regarding the faster replication. Mm-hmm. If you can shed some details, what exactly changed getting the speed up?
Yeah, so the question was if we can go into more detail. This kind of says the agenda slide. I want to give an overview of everything, and I'm going to go into more detail of all these, including that specific feature. So I'll get that in a second. And just for completeness, I'll kind of go over those other features quickly, which is we added support so you can have dual stack IPv4 and IPv6. It's a feature built by Ericsson, well, specifically Victor, I guess, for Ericsson. So that you can be running both IPv4 and IPv6 addresses in cluster mode, and it will return the address that you connected over. And then the other things are just kind of small perf efficiency improvements. Cool. So I'm now going to go into more detail into all of the features we just talked about and talk more about technically what we did to implement them. And what I'm hoping for people to take away here is sort of how we're approaching a lot of these problems. So if you're interested in contributing, you can kind of come help us, or maybe you'll find something that we didn't see. I'll kind of get into a specific example there where we had a really good idea for a feature. We implemented it, and then kind of immediately once we launched it, someone's like, oh, you could have done this better. And it would have been nice if we knew that up front. Cool. So the first thing I'm going to talk quite a bit about is the I/O threading improvements, so the performance improvements. So if you look at Valkey, kind of at a high level, it's basically a hash map. So a hash map, maps a key to a value attached to a TCP server. So we basically read in requests, look up the, go like decode the command, execute the command, most likely pull the data out of the hash map, and then write it out to clients. So we did this almost, I did a talk like this in almost 2020, kind of showing this exact same diagram, which is that if you actually break down where all the time is spent, it's basically all on I/O. So about 60% of all the time that Valkey is spending on the main thread is doing I/O, mostly read and writes. And this is without TLS, so transport layer security. So if you are doing TLS, it's even higher. So the intuitive thing that open source Redis did back for Redis 6 was to introduce the initial version of I/O threading. So the idea behind I/O threading was that we'd be able to fan out the reads and writes. So you can kind of see the diagram here. Everything looks basically the same, except I/O reads are now kind of fanned out. So the main thread's still running. It basically sends a bunch of requests to I/O threads to basically read the data, parse the data, and then give it back to the main thread. So it does this fan out effectively twice, once for reads, once for writes. And the rest of the time, the threads are just hanging out on vacation, not doing anything. So this works pretty well, and you can see it actually removes the bottleneck more or less from the I/O, so read and writes. In this specific example with 2 I/O threads, the bottleneck is still mostly back on processing commands. So it would be ideal if the main thread wasn't also doing I/O. So this gets into the first major improvement that we made in Valkey 8, which is that we decoupled the main thread from having to not be able to execute commands while the I/O threads are running. So this was done with a bunch of lock-free data structures. A mix of lock-free and non-lock data structures. So the I/O threads are basically keeping track of what data they have read and where they're able to write out to. And we make sure that the main thread doesn't push data to the I/O threads if the I/O threads are currently doing work. So this new structure is kind of similar. So now the main thread will still send jobs out, but it's not synchronizing with them periodically like it was doing before. I have a question. Can everyone read this okay, or is this too small? Okay, cool. So the overall structure is broadly the same, and the goal was that this would not it wouldn't change too much of the deep internals. So most of the work was actually done just kind of refactoring the code so that it was no longer accessing very many global variables, and so everything on the I/O threads was able to basically work independently. So this also set up basically a framework for us moving forward, that if there's any work we can offload, we can now send them to the different I/O threads. There is some past work that's very similar inside Valkey, which is doing stuff like lazy freeing of data, which is to say, like, so normally if you're not running with, you can run Valkey in a way so that when you delete data, it's deleted synchronously, but you can also delete it async, so the memory gets freed in background threads. So we can also offload that work to I/O threads as well. So this is sort of a generic framework we built so that moving forward, we'll be able to, offload more work and get the main thread, working efficiently. Go away. I don't know how to. No. Why are you doing this, Slack? Why do you need to update? Go away. Okay. We're on the right side? Okay. So the next thing we wanted to work on was that if you actually now go and do more profiling, you'll find out that there was still more work that we could offload. So what we did was we moved basically everything that wasn't command processing off to the I/O threads, which included some work. So before we'd have to, if you see a Valkey command, it's like set foo bar. So we had the mapping of what is set. Is it a command? Is it a module command? So we moved all of that to the I/O threads to basically get as much off the main thread as possible. And we also implemented a feature called memory prefetching, which I'll talk about in more detail in a second. But the basic idea is we wanted to make it so that we want to set up the CPU in such a state so that it can execute commands as efficiently as possible. Oh yeah, go for it. So there's two questions. One is, when the main thread sends out the send read jobs, when does it wait for them? They basically all get pulled. They get pulled periodically, but you can kind of effectively imagine they get pulled like in the epoll waits state. So they're all being done. It doesn't wait for them synchronously. Like it will keep going and executing commands and then go basically pull more of them. And the second question is, how many is it doing? That's a relatively complicated question. You can go look at the code. It's trying to basically balance so that it's keeping the IO threads busy. So if the IO threads, if it sends a bunch of requests and the IO threads go to sleep, it doesn't actually, like it's most efficient if the main thread does all the work, right? Since there's, if a command is read in on IO thread 1 and then executed on the main thread, they might be on different CPUs, so they'll have different L1 caches. So we want to, so you pay an extra penalty moving the data to the other core. So ideally, we want everything on the main thread. So we basically try to keep the other threads busy, and if we are unable to, we reduce the number of cores. So that's how we determine how many jobs is sent out. Make sense? Cool. And so the last thing we sort of noticed is, so I didn't go into too much detail about what this epoll wait is. So epoll is the Linux functionality to basically, you can tell the kernel whenever you have data to be read or written to on a bunch of different file descriptors or sockets, notify me when there's data to be read or I can write data out. Now, this is theoretically a very fast call, but the kernel actually can do a lot of work during this process to actually figure out if there's data to actually be read. So it will partially do a lot of the TCP read logic to actually read in the packets and figure out if it's readable. So this actually becomes the bottleneck in this new structure. So the last thing we sort of did was offload the epoll system. So now, and so epoll is like our whole eventing system. So it's what notifies us when like we should be taking actions. So now we have this new system where we can actually offload the, when the system is in high enough contention, when there's enough requests per second, like we just talked about, we'll actually just kind of go into a busy loop, basically constantly checking to see if there's data available and sending the actual epolls off to the IO threads to do a lot of the hard work. So this is basically the system that this is the IO threading architecture we have today, which allowed us to get to up to about 800,000 requests per second. So this is, but it's also very scalable. It's like every time we can improve the performance of process commands in this case, the number of requests per second we can do goes up. Because in this case, it's just process commands again, which is the bottleneck, which is what we want the bottleneck to be. Yeah? How do we keep order? So the question is, how do we keep order? And what do you mean by keeping order? So no, there's only one epoll. No, so the IO thread so in this example, IO thread 2 will do the epoll. It'll send the information back to the main thread, and the main thread will re-fan out the request back to IO thread 1 and IO thread 2. So the main thread is still the orchestrator of everything in the architecture. Yeah, there's only one event loop. We did investigate having one event loop per IO thread, but then there was a lot more collaboration that they needed to do. And so when we were investigating that, we found that this was this was more performant. Yeah, so the question was, are clients stuck to IO threads? Today we do, when we accept a connection, we basically, it gets an ID number and we take the modulus of that to assign it to a thread. So there is affinity between IO threads, between the client, but it can move. So as I said earlier, we try to balance the number of IO threads based on the incoming work. So if a client is assigned to IO thread 3 and we decide that's like too many IO threads, so we reduce the number that we're sending requests to, it could move to a different one. So we prefer affinity, as we talked about, so that all of the state stays in the CPU caches, but it's not a strong attachment. Hmm? Yeah, so the comment was kind of about how expensive it is to go between different sockets on the CPU. It's not just having different NUMA nodes or different sockets is like the worst case, but even switching between cores on a CPU is expensive. So typically, like the L1 cache is dedicated to a specific CPU. L2 is normally shared between two different CPUs, and L3 is like shared within the socket. So there's the different like cache layers. So you want to keep the requests being processed as much as possible on the same core. You don't want stuff moving around. Yeah, Vadim.
Coming from transactional atomic world, just curious. So if two different clients request the same data and one client write data, can you get partial reads for another client? I mean, you have complex data structure, and one client updates some part of that partial data structure, and another client read the data structure. Can you get kind of partial reads, partial writes?
So the question is, can we get partial reads and partial writes? In terms of, so the core, like the main part of Valkey is still all single thread. So all the command processing is when we're accessing the main hash table. So none of that can be partially written or read, because that's only ever read from the main thread, which is, kind of keep all that cache locality stuff we talked about. From the data structures that are shared and read by the IO threads, everything has a read. Basically, everything is broken down to the write path, so writing data out to a client, and the read path, reading data into a client. So those all have locks. They're not locks. It's like it's an optimistic, atomic like counter that we check, or a state that we check. So we prevent concurrent modifications through those atomic variables. So there's no partial state that you can read in those cases. Okay. If anyone thought this was very complicated, hopefully the rest of this is a little bit more straightforward. But yeah, that's the goal. We want to, like, if anyone has any ideas of more things we should offload, yeah. Well, how about Kyle told me not to be too technical, but oh, really? Oh, well, I was going to, okay. Apparently I should be more technical. Great. Be as technical as I want. I'm being as technical as I want. It's great. So I mentioned briefly that the other thing we do is this batching and prefetching stuff. So this is sort of what our hash table looks like today. So if you're not super familiar, like when you have a key, you do a hash function on it, and it gets mapped to a bucket, which is what you see on the left-hand side. And then within that bucket, you'll go and basically look into what we call dictionary entries. And within those have a key. So you'll basically go through this linked list of elements and try to see if any of them have the same key that you're looking for. So if we just kind of have an example, if we have a key foo, it might get mapped to bucket 5. And so we'd go and check those two, like the first entry, to see if it has the key foo. If it doesn't, we'll check the next one. If it has it, then we'll go and pull the object and the value out. So you can see here that there's a bunch of sort of random memory accesses, which is to say, you're looking up for some data somewhere in your RAM. And so those are all very slow. They take on the order of a couple hundred nanoseconds, which in the grand scheme is pretty fast. So you don't really notice it. But when you're doing 1 million requests per second, that adds up. So you can kind of see that if we're doing like we can do up to 5 different memory accesses if we're trying to go find a single item. So there's really no way to make this faster, right? We're like, to access the second memory pointer, we have to go look up the first one. But what we can do is we can actually do them in parallel. So when we're doing this memory prefetching step as part of command processing, so the IO threads are giving us a bunch of commands. So one thing we can do is we can do a bunch of them in parallel. So you can kind of see that if we needed to, for example, access all 4 of these entries together, we can basically go pull all of the memory accesses together. Let me go and go back a step. So we can access both buckets together, and these two are now independent. So when the processor doesn't have dependencies on both instructions, they can be executed together, since most modern CPUs are able to access multiple instructions together. And we use the built-in ability to basically tell the CPU that we will need this memory later to basically prefetch it. So and the sample, we can access the first entries together. And then while we're accessing those initial entries, we can go start pulling the next entries as well as the objects, and then pull their data out. So as you can see, this is the same number of total memory stalls. We still have 5 accesses, but we're able to pull the memory for 4 different commands all at once. Yes. Hmm? So I'll answer the second part first. So the second question was, are these being accessed by multiple threads? That actually would not be all that productive because we want the CPU that is executing the command to have all the memory available. So it's only being done by the main thread. So we have this main command execution thread. It's the one doing all of the pulling of memory. So the other question you mentioned, sorry, can you repeat the first question? Oh yeah, the multi-keys, yeah. So the first question was, when are we doing this for multi-key commands or when we have a bunch of different commands? We actually should do it for multi-key commands, and we do. And we also do it if we basically have a structure that goes and tries to pull 16 keys. So the way the batching works is we start parsing commands. So the other thread will send us like 6 or 7 commands, right? And so we start going through all the keys of those commands. And when we have 16, we say this is kind of enough, this is the right number, and we go batch execute these. So that 16 number is sort of magic. It really depends on the CPU architecture. Like, there's no good way to tune it. It's kind of fixed per architecture and like your workload, I guess, a little bit. Yeah, does that make sense? Okay. Yes, it's trying to get everything out into the CPU caches so that all the subsequent accesses are very fast. Hmm? So yeah, the comment was, so this works well if you're just doing pure reads, but if you do something like a read and then a delete, you'll get some of the benefit because you'll still be pulling some of these pointers, like the bucket pointer you'll still be pulling in. So that will still be in L1 CPU cache. But you're right that the deletes will actually kick the data out. But the one benefit of that is you just access the data, you just created it, and you just kicked it out. So although you did a bunch of work, you didn't actually pay that much cost for it to do it because we were doing a bunch of stuff in parallel. So we deleted the data and then we prefetched it unnecessarily, but it actually won't do too much of a cost because since all of the pointers will be in the L1 cache, we'll be able to access subsequent stuff very quickly. So ideally we would have this like complex logic to find these dependencies and like not do unnecessary work, but in practice it's a lot of code and the performance benefit's very small. So the other thing I'll say is like, we really only did this to optimize for the common caching, get, set, delete, expire type cases. There's a lot more work that could be done on some of the other data structures, like skip list is sort of notorious, which is the data structure backing the sorted set. There's a lot of random memory accesses that we don't need, and so we could very much highly optimize that with this type of pattern, but we haven't done that yet. So there's a lot of work to be done. Do you know, Victor? I always get this wrong.
So if you wanted 1,000 keys, when you get 1,000 keys, you rehash?
I thought we start rehashing at 0.5. I thought we start rehashing at 500. We try to keep it very low because having to do 2 entries is very expensive. Or maybe 0.75? I think the question is, what's the load factor of the real hash table implementation we use? And I thought it was...
When we do the rehash, right, we create integer one.
Is that what I'm saying? Right. Yeah.
If you go to 300, what you're proposing, what we're doing here would be a lot more beneficial if it's 100%.
Yeah, so we were kind of talking a bit about the load factor, which is at what point, at some point, if we fill this entire hash table up with entries, we'll need to expand it and add more buckets on the left-hand side. That process is called rehashing. So we rehash, apparently when we release, like when there's the same number of entries as buckets, we start the rehashing process, except for some cases like doing a fork during replication. Yeah. Do we have a second microphone by chance? No. I think, yeah. Yeah, it's better because like they just had a conversation, so I'm not going to repeat the whole thing, but I could do this. So we can start doing this. Thank you. Okay. Can everyone still hear me? Am I about as loud as I was before? Okay, perfect. Okay, any other questions about all this stuff? This is the most complex thing that I'm going to talk about.
And I might be misleading here, but I recall. Yeah, sorry about that. Does that divert from what Redis uses? Because in my mind, for some reason, I was thinking about the try map that was used to hold all of the mapping between the keys and the values. So just out of curiosity, are we diverting from Redis, try map, and hash map?
So yeah, so Redis uses something called a radix tree, which is kind of like a try. And so it used to use a radix tree to map the key to slots, and that was changed in Redis 7.4, and as well as Valkey 8 to be, no, sorry, that was changed in Redis 7 to be a linked list that basically we kind of created this giant list that mapped all of the keys together. And then in Valkey 8 and Redis 7.4, we now have like a dictionary for each slot in cluster mode. So there's no other radix tree mapping the keys today.
What was the reason to abandon that data structure?
So the radix tree is, although it's pretty memory efficient, it's actually very CPU inefficient. So I think we cut off like 5 or 6%. Well, so no, it was both memory inefficient as well. I think we could have made it more efficient, but I think it was easier to just move to, like, we didn't need the sorting. So one of the benefits the radix tree provided is it's ordered. We didn't need that ordering, so we were paying costs to maintain that. So that's why we got rid of it. So the new structure is unordered. Okay. So apparently I have 5 minutes left. I've been going way more than I expected. So here's kind of a summary of what we just talked about. You can see the performance improvements between Valkey 8 and Valkey 7.2. We were able to get about 360,000 requests per second with multi-threading, up to about 1.2 million requests per second. This is done all on Amazon Graviton hardware. So the performance you'll get, it definitely depends on the type of hardware you're using. So results may vary. Okay, so yes.
Do you have any recommendations for how to set the value of our threads based on the total threads on the CPU? Because after a while, I imagine you get diminishing returns.
Yeah, so you'll get pretty close to linear performance up till about 4 threads, and then you'll get diminishing returns up to about 8, but you'll still see pretty good improvements. It really depends. Like you shouldn't launch a bigger instance to try to get better performance up to about 4 threads. And you also have to remember that you're competing with other processes like background saving as well. So that's probably, think about that heuristic. So probably around 3 or 4, and then have spare capacity for forking. And if you need to scale up a little bit more, then you can add more threads as well.
So to get that 1 million, how many IO threads were there? 4?
I believe there's 8,
Oh, 8.
because that's sort of where it taps out. I
So-
believe
so-
4 will get you somewhere close to about 1 million.
So it's like this, and then you kind of plateau.
Yeah, it's like up. Yeah, it's about linear, and then it flattens out, kind of curves off.
And
That's true. There's 2 blog posts that I think are called Achieving 1 Million RPS, so you can check those out on Valkey.io to get more detail about the specific details. I don't think we have a curve, though. I think we only tested it with 1 amount, but we can also do that. We also have had a bunch of people ask for this type of tuning blog to like figure out what's the optimal number of threads to use.
The current implementation automatically reduces the number of threads if the load is a bit lower, right? So it disables them, kind of.
Yeah, but most people would probably like allocate a number of threads to like the process, so you don't want to over allocate threads because then you're just not having idle capacity
When
on
you
those.
decide how many CPUs you want in your instance, yeah.
Since I only have 5 minutes, I'm going to skip over the memory efficiency stuff. If you want to ask me about it, you can come talk to me later. I guess this is the TLDR. You can see a bunch of memory improvement, great stuff. But since someone specifically asked me about how replication is better, we'll talk about that first. So today, when you're doing replication between a primary and replica, it basically happens in 2 stages. There is the full sync, where we do a fork, and then we generate what's called an RDB file, and we send that RDB file over the network to the replica, that loads that data in, and then we send an ongoing chain stream of individual commands, which then get applied on the replica. So the main thing that's different in Valkey 8 is we now send these across 2 separate channels. So while the full sync is being generated and sent, we open a second connection and we send the ongoing change data capture to the replica. So instead of buffering those commands on the primary, we buffer them on the replica. So yeah, go for it. There's a
Regarding the full sync transmission, are you sending the RDB as it's being constructed, or are you waiting for the full RDB to be constructed on the primary prior to sending it over?
So there are 2 ways today. There is basically where we first write it to the disk first, and then once it's fully written to disk, we send it to the replica. We can also send it to the replica while it's being generated. There's one other nuance to this, which is it's kind of hard to capture, is that we made a change in Redis 6, I believe, so that when we create the snapshots, we actually send it first. So when you do a fork in Linux, you have a parent and child process. The child process is the one responsible for generating the full sync, but it actually sends the full RDB file first to the parent process, and then the parent is responsible to sending it to the replica. And this was to support TLS at the time, so that only one process was responsible for the encrypted state. We now no longer have to do that. So both the child owns the full sync states, and the parent owns the change data capture state. So it's also about 30% faster, in addition to being able to send it across 2 channels. Make sense? Cool. How much time do I have left, Katie?
You're a little bit, I think we're right now.
Right now? Okay, so I'm just going to go over the rest of the things, and if you want, I can go show these slides and kind of while we're having coffee or something. So the other big thing that we improved was what we talked about was with the migration states. So before, we had a system where you had to basically orchestrate the migrating of data from 2 primaries. And if the primary failed during the process, you would have to basically resume it. So we built a mechanism to synchronously migrate the replication state to the replica so they could participate in the migrations. Super exciting stuff. It's so exciting. Definitely come ask me about it. I talked a little bit about the slot statistics, so you can kind of see what it looks like. You have the ability to basically ask a node, hey, which slot you have has the most keys in it, and it will tell you which slot has the most keys, where before you had no idea. We also added a bunch of more metrics towards individual clients. So this is what you get if you do client lists to figure out which clients, like it dumps all the info about clients. And the last three fields, the network bytes in, network byte out, and total commands are the new metrics. Super cool. If you're interested in any of this stuff or want to ask or want to get involved, the three main ways, you can go to Valkey to learn about this stuff, try it out, or this is our main GitHub repo, and you should have a link to the Slack, which is the main way we discuss, well, we discuss stuff on both the GitHub and the Slack. So I think that's everything that I have. So thanks for listening to me ramble about a bunch of tech stuff, which I think is really cool. And enjoy the rest of the talks.